What is optics? Optics may refer to the scientific study of light, but often optics refers to optical components, like the lenses shown on this slide. The discipline of optics is at the intersection of quantum mechanics and electromagnetics. Quantum mechanics is the study of discrete things. Electromagnetics is the study of continuous field distributions. Computational optical imaging focuses on discrete computation, but the physical interface of computational imaging systems relies fundamentally on analog processing in lenses, coated apertures, and filters. Today we begin discussion of Chapter 6 of Computational Optical Imaging, which discusses coherent imaging with optical elements. Amazingly, we're halfway through this course, and only one of our lectures so far has focused on lens design. Today we start to make up for lost time. Computational Imaging. Episode 35, Optical Elements. Chapter 5 of this course focused on field propagation. So given the field distribution on an input plane here, f of x, we could calculate the field on an output plane, g of x prime, y prime. In episode 34, we talked about what happens if we have an inhomogeneous media in between and how we could use a characterization of the inhomogeneous media to form a turbid lens to actually image by measuring the modes through the turbid media. But of course, it's much wiser to create optical elements that code the field for imaging, and that would be things we'd put here at this plane, x prime, y prime. So the problem we're interested in today is we have a field that propagates to an optical element, such as a lens or a prism or a diffraction grating, and then propagates from the optical element to the output field, and we'd like to characterize this input-output relationship using field theory. Back in episode 25, we considered this system with rays, and we considered that for a lens, all rays that come in parallel to the optical axis, for example, cross through the focal point. Today, we want to reconsider this system and other systems using wave theory. Now, in addition to the reflection and refraction behavior that we can see with rays, when we look at the field theory of optical elements, we'll also see diffraction effects and interference effects that are more difficult to explain from ray theory. So let's begin like we did with ray theory and start by talking about prisms. So a prism is a wedge of some high index material that we're going to use to modulate the field. And so as the field comes and propagates through the prism, it experiences a path delay at various points in the prism. The thickness of the prism we can write in this form. So delta naught would be the thickness at the thickest point, and then as x increases vertically, the thickness decreases linearly. And so we have this model for the thickness of the prism as a function of x. And then we can measure the optical path length through the prism, which right here is phi of x. So in the part of the prism that's air, the index of refraction is 1, and so the optical path length is the thickness of that part of the prism divided by lambda. So here at the top of the prism, it's going mostly through air, so this delta naught minus delta would be equal to delta naught, and so the optical thickness at the top is going to be delta naught over lambda. But as we go toward the thicker part of the prism, more of the prism is going through the high index material, and here the wavelength is lambda over the index of refraction n, and so the optical path length is longer. We can simplify this expression as shown here, and then an optical wave coming in and incident on the prism experience a phase delay proportional to the optical path length. So we can take this optical path length and take its exponent, and that's the phase modulation we would have modulating an incident field. And we would describe the effect of the prism on the incident field by what we'll call a transmittance function. Now, of course, what actually happens in the prism is a little bit more complicated because the field propagates in 3 dimensions. But for thin elements, we can ignore things like the tilt of the wave as it goes through the material and just assume that we have a model of the instrument as a 2-dimensional phase modulation of the incident wave. Now, a wave incident on the prism, like this wave, we have a wave propagating with angles theta relative to the x-axis. So here would be theta, and we have a wave coming in. It's going to strike the prism and be modulated by this phase modulation. So we would multiply the incident wave by the phase modulation of the prism. And what this does is it changes the transverse spatial frequency of the wave so that the wave is refracted by the prism so that it would propagate down in this case. And the new horizontal wave number would be the the sine theta over lambda from the original wave, and then minus this part 2n minus 1 times delta naught over a, the extent of the prism for the vertical part. So we have this 2n minus 1 delta naught as our new wave number along the x direction, and the angle of the refracted wave now will be this theta prime as expressed here. So the effect of the prism is to redirect the incident wave. Another kind of optical element would be a diffraction grating, which we could look at as kind of an array of prisms, thin elements with some kind of wedge behavior, but now the angle of the surface is changing as a function of x. We don't have a constant modulation of the surface as a function of x. In this case, we assume a periodic modulation of the surface. So we'd have, for example, that the surface normal of the element could be changing sinusoidally as shown here. So this now is going to have a transmittance function which goes like this sinusoidal modulation of the surface, because the thickness of the material would be changing sinusoidally as well. And so the transmittance function would have this periodic form instead of the linear phase term that we had with the prism. So this is a periodic modulation, but it doesn't, so the change in the wave vector we would have this sine kx added to the incident wave vector, which is actually multiple wave vectors, that the periodic function e to the I sine theta x can be written as in a Fourier series, because sine kx is periodic. In this case, this is the form of the Fourier series describing this e to the I kx. And now the diffracted field is the incident field times this transmittance function, and the transmittance function has multiple periodic components. And so what happens is the incident wave comes in and it gets diffracted into multiple orders, where each order has a component of the grating wave vector, which is k here. And so the diffracted field diffracts into multiple orders, the 0th order corresponding to the DC component of the phase modulation, and then each higher order having a wave vector which would be q, an index divided by lambda, the period of the grating. And now the diffracted, each order has its own diffraction angle, and the diffraction angles of each one is shown here. The wave vector of the diffracted fields have the transverse component added with the wave vector of the grating added to the transverse component. And here we assume the grating is just along the x-axis, so the y component of the incident wave vector is not changed. And then the z component of the wave vector of the diffracted wave has this form. Now, if it happens that this q gets large enough that this square root becomes imaginary, then we get a evanescent wave. So the wave would decay exponentially. The wave vector is at such a high frequency in the transverse direction that it doesn't propagate in the z direction. Okay, so these are two effects we have in optical elements. We have talked about refraction, like in prisms, and now we see these diffractive effects from the structure of the material. This is what these effects look like physically. Now, with the prism, the diffraction angle depends on the index of refraction, but doesn't explicitly depend on the wavelength of the field. But here we see a prism illuminated by a white light, and then we see colors coming out as diffracted. The color separation in this case is due to the fact that n, the index of refraction, is a function of lambda. So this is materials dispersion causes the colors to separate on refraction by a prism. And when we get to lenses, this is called chromatic aberration. The difference between the angles of refraction for different colors causes some color separation that we'd like to fight against in lens design. For a diffraction grating, the wavelength dependence is more explicit because the diffraction angle is linear in the wavelength. And so as we look at a white light incident on a diffraction grating, you see the diffraction into multiple orders. The 0th order, the grating is basically acting like a mirror, so the colors are not separated. But as we go to higher orders, we get a higher color separation, as shown in the diffraction fields here. And this faster diffraction due to the structure of gratings leads gratings to be more powerful in building spectrometers than prisms, although both have a role depending on the amount of materials dispersion or the amount of chromatic dispersion that one seeks. Now, with these diffractive effects, so with the prism, of course, we're using the index of refraction of the material to process the optical field. With the diffraction grating, we're using the structure of the surface. You notice that the diffraction angle doesn't depend on the index of refraction. It doesn't have a materials component in it. And we can create all kinds of optics by using this kind of structure to create optical forms. This is the discipline of metaoptics, or diffractive optical elements. So, conventional lens just uses refraction. If we have a wavelength structure that's larger than a wavelength, that's usually referred to as diffractive optical elements, or on the wavelength scale. If we use materials resonances using components that are where the component in free space is smaller than a wavelength, although the inside the material size of the material could be on the wavelength scale of the wavelength inside the material to create kind of resonant effects. Then you have what's called a metaoptic, and we can build lenses by refraction or by these kind of modulation of the structure of a material. And metaoptics, currently uses things like these nanostructured surfaces. Here we have nanodiscs and little bars that are created out of refractive materials to create structured behavior in the optics. You can use this, of course, to create diffraction gratings, to refract light, to bend the direction of light, or to create lenses. But you can also use these metasurfaces to create arbitrary field surfaces. So if we illuminate with a plane wave, in principle, we could create a arbitrary field distribution on the surface of the optic, and then have it diffract into whatever kind of pattern we like. This is called computer-generated holography. Here's examples of the use of metasurfaces to create computer-generated diffraction patterns. So that's an introduction to the basic mechanisms of optical modulation and optical elements, refraction and diffraction and interferometry inside of the nanostructured shape of these metaoptics. But what we're most interested in this course is the functional utility of optical elements, which for most cases in optical imaging is to form a focused image of the remote object. And for that, we use lenses. So we can also build this kind of transmittance model for how a lens works. Same as for a prism. We have the idea that there's an optical path length through the lens, phi of x, y, and it follows the same basic forms we have for a prism. The main difference with a lens, of course, is that with the prism, the thickness is changing linearly in the transverse direction. With a lens, we have spherical surfaces typically, and so the transmittance changes according to this square root form of radial distance from the center of the lens. But this is often approximated by a paraxial approximation, and so we get a quadratic modulation of the optical path length through the material. If we have a lens with spherical surfaces with radiuses of curvature R1 and R2, this is the form of the optical path length. And this term, 1 over R1 minus 1 over R2, where R1 is the radius of curvature of the first surface, R2 is the radius of curvature of the second surface, we can abstract out, and we'll relate that to the focal length of the lens. As we saw earlier in modeling diffraction, we saw that if we have a chirped field distribution, that field distribution focuses, and here we're using this optical element to create a chirped field distribution, and so it's going to cause the material to surface, or the material to focus at this focal length f. We take this n1 minus 1 over r1 minus 1 over r2, and we call that the focal length. And this relationship between the radius of curvature of the surfaces to the focal length is called the lensmaker's equation. Now, this course is going to deal primarily with optical processing in optical elements, and so we won't deal with the details of lens design. Actual lenses consist of multiple elements to fight against chromatic aberration, like we saw with the prism, but also to fight against geometric aberration, that the approximation we made here, the paraxial approximation, has a limited range of utility. And so lenses are described by entrance and exit pupils. And what we'll be mostly focusing on a model of how the lens behaves after the exit pupil. So we'll have kind of an abstract model of a lens. But we appreciate that a lens has a focal length and has this property, like we saw in our ray tracing analysis in episode 25, that it can collimate light or bring light to a focus. Now in this case, if we have an impulse, one focal length in front of the lens, so we're one focal length away from the lens, that impulse could be described in the Fresnel approximation by this field. And now if we modulate that by the transmittance function of the lens, it would cancel the field distribution of the impulse and create a collimated beam with just this e to the I kz dependence. If we move the impulse off axis, so now the impulse, instead of being centered at x is not equals 0, is shifted at some other range, then the diffracted field will have some quadratic phase modulation from the position of the object, but as a propagating field as a function of xy is now a plane wave, but tilted at some angle x naught over f relative to the optical axis. Now, there's one problem with this transmittance function is that what if we let xy become large, then the separation between the planes goes to 0. And so we have to do something to kind of limit the range of xy. And we do that with the pupil function. So in addition to the quadratic phase modulation of the lens, we recognize that this quadratic phase modulation is going to apply over a finite range of x and y. And so we limit that range using the pupil function. And this usually corresponds to the aperture of the lens. So if we have a lens with circular aperture diameter d, the pupil function is going to be a circ, meaning that the transmittance of the lens is 0 outside of the pupil and 1 inside of the pupil. Okay, so that's our basic description of optical elements. That now we're going to describe lenses for the purposes of this course as things that modulate the field with a quadratic form. And so if we have a remote object, what we would like to see is after the lens, the field would be formed into a quadratic beam that focuses at the image plane. And so with our next lecture, we'll talk about the Fourier theory of lens imaging and how we can understand the process of image formation in a wave theory using lenses.